I'm here. So the next speaker is Richard Green, who was a student at Caltech, and Maarten Schmidt was his advisor, and he graduated in, when? 1977. And he worked on quasars and white dwarfs, dwarf stars, luminosity functions, and so on. And he went to the University of Arizona, where he, in short order, became a, I was going to use the word administrator. It's a good title in this case. He was the director at Kitt Peak National Observatory and with the Large Binocular Telescope. And recently, he gave all that up and is back looking, I suppose, at quasars. I'm not sure what he's exactly doing. Still luminosity functions, I expect. So anyway, Richard has been very prominent in astronomical circles for the last 30 years or more. And he's going to talk to us today on the quasar luminosity function. Then and now.
Thanks very much, Marshall, and thanks to George and the organizers for creating this great occasion for us to celebrate Maarten's intellectual legacy here. So I'm going to cheat, of course, on the 50 years because a luminosity function requires a statistically interesting sample of objects, which took Maarten and others a few years from the year of discovery in order to actually get things going. And so for some definitions, the quasar luminosity function is, as you know, well, what was then? Then Maarten launched a certain graduate student on a large piece of work because the status of optically selected quasars was not very well known 40 years ago. And it was about 10 years of work. You notice Maarten was having discussions with Alan Sandage even as the results of that work was coming out. And I will concentrate more on now, namely what is the state of play of the quasar 1 luminosity function. And I'll give you my view of the issues. And this is likely to serve as an introduction to many of the topics this afternoon. So it will be very broad brush. If I got it wrong, I hope you'll jump in. If I got it right and you disagree, it will point out that the field is still lively, and that's good. A broadline quasar. So you've been hearing the intellectual context, which is easy enough to forget, but it is certainly true that almost all the early papers had to have some discussion about whether these objects were actually at the distances indicated by their redshift. That's a preface that's no longer required. And not only was there this question of that kind of placement in the universe, but there's the question of could a population be evolving that rapidly? Because Egan, Bell, and Sandage paper was very influential in setting the context of what today we call passive evolution, that galaxies and all the structures formed relatively early on and were slowly evolving with time. So finding this disturbing population that seemed to be evolving very rapidly actually ran into some traffic. So some things remain constant but have become much more sophisticated. So the earliest complete samples were from the IDs of radio sources, and then since those almost without exception showed a rather strong bluer than stellar color, it was easy enough to try to cull them by looking for ultraviolet excess, plain and simple. And so now, as people recognized from the heritage that Maarten established, the selection function is all. You really, in order to have a valid sample, you need to understand the limits up to which you could have found the objects so that you define your boundaries very cleanly. That's now a very sophisticated procedure, and any modern paper is going to have a long appendix about how a color selection was derived from a distribution of quasar spectral energy distributions with emission lines superposed and at the redshift limits that Don will talk about, the actual distribution of Lyman alpha forest absorbers matters in terms of defining the limit on your sample. You heard correctly that these were known to be variable objects, and of course, some of those early radio sources were optically violently variable objects, but the other kind of selection technique that's in use, some now with the repeated painting of the Sloan Digital Sky Survey, Stripe 82, and the anticipation for LSST and Pan-STARRS, will be that it can also be selected by variability properties. That is also a long time endeavor where Sandage had photographic type variability data, and Peter Usher, among others in the very early days, said, again, what's the selection function? How do we decide what's actually variable? And developed relatively good usable samples out of that. So we had to move forward a bit beyond 50 years, but Maarten in 1970 derived a quasar luminosity function, and a function that described a distribution of radio to optical power, which turned out, it was a good trial model and turned out not to be validated, but fine. However, those were pioneering days. This was a sample of 20 objects each of optically selected and radio selected. And, surprisingly, Maarten noted that further identifications in spectroscopic work, especially at visual magnitudes up to 3 magnitudes fainter than the current limit, are needed. This theme has not changed in this field at all. More data are always required and fainter than you can now go, no matter what you want to do. It is interesting to note, however, that the magnitude limit has moved from a bit beyond B of 18 to 25th magnitude IAB for the cosmos field, and a sample of 40 objects is now, the biggest case is 58,000 objects, so the level of statistical validity has actually moved a great deal in those 40 plus years. And the other constant in this type of investigation is where the data are good enough to have a statistically significant result, people tend to get the same answer and at least agree on the qualitative conclusions. And at the ragged edges where the samples are small, there's lively controversy because that's where the interpretations diverge. Maarten pointed out that his average of V over V max greater than a half implies a non-uniform space distribution, no matter whether it's local objects or cosmological objects, and that is still true in the samples that you see out to at least redshift 2. And going to higher Z, which Don will cover in much more detail, a turnover was identified, and something changes between 2 and 3.5. So in those old days, in the end, after 10 years of work, we had a princely sample of 92 objects, and the kinds of models that seemed to fit were that the characteristic luminosity, in other words, there was a steep fall off to very luminous objects and a rather flatter part going to fainter magnitudes, and you could define the knee with a characteristic luminosity, and that seemed to, that certainly evolved with redshift, and the best fitting models had that luminosity-dependent density evolution where there was a coupling between the shape and the evolution. But things have moved on, and there are massive surveys that have been undertaken since that really redefine the shape of the field, like 2QZ, like SDSS. And so I'm going to quote a lot as a snapshot from Nicholas Ross's paper that came out this year, and pure luminosity evolution may actually be working, but you can decide. And the field of play has moved to high redshift and faint objects, as you'll see. So here's a forbidden eye chart. We're not supposed to make view graphs like this. The point of this is that every line is a major determination of some portion of the quasar luminosity function over the last dozen years. And so this is now an exceedingly, this is again from from Ross in 2013. And again, you know, this shows you that this is now a major field of endeavor to try to understand quasar demographics based on statistically well-chosen samples that can then be modeled by some simple kinds of functions. And what intrigues me, of course, is that in NQ, which is the third column, the biggest entry is the Yeshen and Doug Kelly's compilation based on a mere 58,000 spectroscopic redshifts or thereabouts, and samples of 20-some thousand are relatively routine, that the typical magnitude limits are down at I or R of 20 plus, and that the redshift range can range anywhere from here to 6. So, you know, this is serious work. So what is the state of play? Well, here is Ross et al., which is based on the Sloan Digital Sky Survey Data Release 9, and the addition of a very large sample from the BOSS, the Baryon Oscillation multi-fiber runs, for which quasars were specifically targeted. And you can see, right, it intrigues me that in the upper left, those are the statistical error bars. They're just inside any point you wish to plot. So, you know, the samples are superb in determination. And you can see that over this range, the shape is relatively well preserved as the sample crawls to the right, meaning that in general, a snapshot in a given slice of cosmic time showed you quasars that were significantly brighter on average. And if you take what is the industry standard thing to do, namely fit 2 power laws with some kind of break in between as a parameterization of a curve, then you find that their claim of pure luminosity evolution says that the slopes for the faint end, which is alpha, and the bright end, which is beta, are really consistent with being constant up to redshift 2 or 2.5, at which point things start to change in some interesting way. And in the upper right-hand corner, you can see their derivation where the characteristic luminosity, the knee at which the break happens, increases to brighter and brighter magnitudes as a function of cosmic time as parameterized by redshift. So this is fairly decisive. And the other thing you note is that in that model that just glides gently to the right up to redshift 2, the normalization at that point, by definition, stays constant to redshift 2 and then plummets. And so there indeed, even the number of bright quasars is apparently dropping off as you go back in cosmic time from the peak of activity. As many authors and many sitting in this room have pointed out, and so here's the realization from these optically selected data. There is an effect of cosmic downsizing, which is that as you go to fainter absolute magnitudes, meaning going upward in color on that graph, the peak of incidence of such kind of quasars moves forward in cosmic time. So you can decide where the peaks of those curves are, but you can see that from minus 28, which is one hefty accretion event, the peak is sitting at around redshift 3 or thereabouts, and at minus 24, you might move it below 2. So that the typical quasar event, whatever it is lower power as you come forward in cosmic time. The situation becomes more complicated as you go to higher redshift, and Don will talk about this, but here's Ian McGreer's paper led also on Sloan-based data and some specific spectroscopic follow-up. So the red points are a fair investment in large aperture time that they've made to identify an interesting sample at redshift 5, and plus or minus a bit. And you can see again 2 power laws fit perfectly well to that, and so it's fine to parameterize things that way. It's just that the red points didn't exist before this survey paper, and so people were fitting to or some combination of orange and purple, and were thinking that the bright end was actually flattening off as you went to higher redshifts. And their claim would be that that's really not the case, that what's going on is that they did define the break. The break luminosity continues to rise with redshift at least up to 5, and the handful of objects denoted by the purple star at 6 may show you that finally there's been a limit to how bright the typical quasar is in a quasar event. But that's a somewhat different and new answer from early smaller samples. Again, a sign of it's controversial when you don't have many data points. And the perhaps disappointing news is that the normalization at the break continues to plummet to the point where if you integrate the brightest quasars down to an absolute I magnitude of minus 24.5, you drop by a factor of 6 in density, or 6.5, from redshift 4 to 6 or something like that. And so that makes the predictions for the redshift 7 and 8 blind searches a little bit dismal in terms of the return that they might get. So that's an interesting outcome. Well, let's go back in time, because the sample at redshift 6 was 9 objects. The redshift 5 one, they added about 80 objects. And so at the redshift frontiers, or more to the point, with people finding exoplanet configurations of certain orientation, the samples are really small, and it's really exciting because you found the greatest redshift. You found 5 planets in circular orbits. You know, this is the edge of discovery space today, and it was as exciting. That's really a then picture on the right, and I bring it up because that excitement was just ubiquitous. I was working at my desk. I had 2 pictures on my desk. I had a picture of my then fiance and now wife of many happy years, and on the left, the very first bright quasar that Maarten and I had confirmed in this new UVX survey. So Ed Turner's wife Joyce walks in and looks, and I swore she was looking at the left-hand picture. She says, "Wow, that's really exciting." I said, "Sure is, and she's really bright." And and I hope to get a whole lot more. My second digression that I just can't resist is that this UVX survey that Maarten and I took was hard work, and it was based on really tiny photographic images from Zwicky's 18-inch Schmidt, and so the measurements were hard to make on those photographic films for every reason that Maarten talked about. And so for years people said, this just can't be right. You know, you have to have missed most quasars. So to our joy, a postdoc with the SDSS project in its early days said, let's go back and look at this and see how you guys really did now that we have ground truth. So Sebastian Yester engaged a number of his colleagues, and to our happiness, he actually found results that were all perfectly reasonable. One is Maarten and I had a sparse enough grid of photometric standards for calibration that we fit a linear range of photographic magnitudes and extrapolated off either end, bright and faint. And you know, photographic transfer curves are what they are, and it should be curved. And so now that the sky was full of SDSS stars for great photometric calibration, he applied that curve and got some shifts in our magnitudes and colors, not surprisingly. And because we ended up being so conservative to try to stay away from the stellar locus, just as our friends fishing out redshift 3 quasars need to do, and we found out, even though we thought we were making a color cut to encompass most known quasars, we were in fact cutting about a quarter magnitude bluer, which is right in the middle of those unobscured quasars. But the good news was that there were no other systematics, because he did a cross comparison with color, redshift, radio properties, and from an SDSS subsample, which was only mildly overlapping. And so we may have missed by some factor, but not otherwise skewed the conclusion. So that was quite interesting. So it was heartwarming also. Okay, what did we know then? Well, Donald is here. You knew that the power requirements and the short variability timescales just required accretion in a gravitational potential, period. Dynamical measurements indicating that central black holes were a reality were just getting started at about the same time. So there's Sargent et al.'s paper on M87 in 1978, Peter Young's thesis in 1979. So these were early days thinking about what was then the distant universe and the local universe. And Zoltan's argument, which is the integral equations, basically saying if you sum up all the mass in black holes then, whenever then was, what's the local space density, mass density of black holes now? He made that argument. But it took about 20 years to find the local black holes and tune up the high-Z quasar luminosity function enough so they realized that, yes, the argument is correct and there's actually observational evidence to support both ends of it. We're going to hear this afternoon from Brad. Reverberation mapping was also just gearing up by him in the 80s. It had been pointed out earlier, but the time monitoring programs were just getting started. His 88 paper is a review on why it was hard, which it was, and so that was just getting going. Now, the broad line width is the standard measure of a black hole mass in a quasar, and it has a huge rich literature, and I'll just point out a paper coming out by Wenwen Suo from PKU, where she's gotten a sample here at Palomar of redshift 4 objects to make sure that H-beta, magnesium-2, and C4 are behaving as you expect. Now, okay, editorial comment, there's still a nagging doubt. There is a Baldwin effect. And so what happens when those line coolants saturate? Do you still have the same geometric distribution of emitting clouds? Or is there a bending over in some other physical property? So it's an interesting question as whether you can tie in the high redshift, really luminous quasars that people are now observing. I won't push that too hard. The real issue here is it's very nice to select by UVX, by broad lines, by variability with a straight-in shot to the nucleus. What about that whole other population that, for some reason or another, you just can't see? And so, again, going back to the intellectual context, Einstein launch was in '78. IRAS wasn't launched until 1983, and Antonucci and Miller presented their results of discovery of a broad line spectrum and polarization in a CFER2 at the Tucson Winter Meeting in 1984. So thinking about papers published in the late 70s and early 80s, this was not a key part of the thinking just yet. So, the ways to go at it are hard X-rays and far IR to figure out what that population is. Dan Stern's going to tell us, he had a wise selected sample of cosmos quasars that were relatively bright, and that gives you a measure that obscured to unobscured is likely to be close to 2 to 1, at least at a bright limit at a certain redshift. Maguri and her collaborators have been working on this from the hard X angle for a long time, and I suspect she'll tell us more about that. I picked a Günter Hasinger graph or two just to show graphically what is going on, because he amalgamated some samples and showed that there's a huge correlation between the obscured fraction and the total X-ray power, which is intuitively pleasing because you might think that the more powerful objects sort of clear out more of their sky so that you can actually see what's going on. And he finds, when he makes some correction, that the obscured fraction also goes up sharply with cosmic time and then saturates out. So that there is a big population that these beautiful, high statistically significant curves don't take into account. And so in many parts of the diagram now were systematics dominated rather than population statistics dominated. That's interesting progress for sure. That concept that there's part of the sky that you don't see from the quasar was validated from a interesting sideways route where Hanaui and Prochaska looked at a sample of quasar pairs very close by each other, a foreground and a background. And so you're looking at the gas in the vicinity of the foreground quasar probed in absorption by the background quasar. And they almost never see high ionization systems that you would expect if you were looking down the UV nozzle of some accreting quasar. They're mostly low ionization systems. So for most of the sky, the quasar radiation isn't seen in its own vicinity. So that's a validation of this fraction, the saturation fraction of about a factor of 2 at a certain redshift range and so on. Okay, so the other thing that's new in this field is that with the sophistication in computational astrophysics, you can now actually say, what do all these quasar demographics mean in terms of galaxy formation, in terms of what's going on in the earliest universe? And so Phil Hopkins was a real pioneer in this, and there is now, again, a really rich literature talking about things. So there are 3 types of models. One in which you all physics all the time, where you put the quasar physics in the hydrodynamic simulations and see what you get. One is semi-analytical prescriptions for following processes of what the quasar is doing while you're forming galaxies. And finally, the use of relations between black holes and halos and having an interaction-based kind of model. And so quickly, here's a couple of slices that from Ross et al. Again, and just showing where things go. So the black region is the hydro simulations with quasar feedback. Those are the physics-based models, and they mostly hit the region. The green line is semi-analytical prescription that was tagged onto the Millennium simulation for galaxy formation. Fanadakis et al. Is a semi-analytical approach with a different galaxy formation scenario where the triggering can be also based on local disk instabilities to get gas to flow into the middle. And Conroy and Wright tie things more to halos and less to individual physics of the local sources. So those models are likely to make different predictions about shape of the quasar luminosity function, depending on whether it's mergers or cold flow into the local potential, or whether it's local disk instabilities. The high redshift luminosity function observers feel that they're going to be able to constrain those models because there was a lot of action between redshift 6 and redshift 3 and in a short time. And so the shape of the LF might tell you something. The lower redshift folks, as things slowly exhale, are less sanguine about what they can do because, the occasional major merger, the occasional disk instability, it's going to be more challenging to decide what sets the shape. Okay, we started 5 minutes late, so I'll take a little bit, which is a complication to all this is if you believe that cosmic downsizing is because of mergers and interactions with halos, you might expect that a lower power object with a lower mass black hole is going to be in a lower mass halo with lower clustering amplitude. And the tough thing is that here's an example from Tom Shanks and his crew with the 2QZ and 2SLAC and so on. They have a correlation, quasar correlation function. That was unimaginable in the 70s. And here you see it. Now notice the scale is megaparsecs, so we're not talking about so much individual clusters as large-scale clusters. Even so, there it is. And if you take a value for that at near the knee, you see that there's next to no evolution between 0 and 2.5. And so that's a bit of concern, or maybe it's telling us something relatively profound about the relative role of mergers and other things in making a quasar. Oh, that went too fast. Okay. So I'll wrap up by saying that this is still a lively, exciting field that's very future-looking. The work's now getting hard because the interesting parts of the LF that are not populated are faint high redshift or both. And there's lots that we would like to know. If there's this healthy population of high redshift quasars, you've grown them up from nothing in a very short time. And so we're already getting into trouble with Eddington limits. And so what is the distribution of seed black hole masses, and can you actually derive that? We'd like to know. We'd like to know the relative contribution of major mergers, of cold flow, of local host galaxy instabilities, because that's really telling us about the growth of black holes. It would be interesting and could be done to actually include some prescription for all quasars, including the obscured ones, before you start fitting to models, and so that may be informative in and of itself. And we note that the integral of the luminosity function, even if you fit it with a power law that's relatively steep, isn't going to diverge. And so there's a whole unexplored region of where does that actually turn over, because most luminosity functions actually drop off at the faint end as well as the bright end. And so what's that telling us about the physics? Is there a predictable transition from thin disk accretion to ADAF or something that might inform us? And can we observe any population to faint enough levels to actually find that? So we owe a whole rich field of endeavor to this man who applied his classical training in galactic structure, and he applied this technique with rigor and imagination. So this is a great tribute to Maarten.
Thanks, Richard. So I guess we have time for one, possibly two questions. Who has a question or a comment? We're all overwhelmed by the thoroughness of your talk. Okay, thanks very much.